Hello there, this is Mr. Marek. In this video, we are learning about electric circuits. We're learning just the basics to begin with, but there's still a lot of information that we're going to go through in this video. So it's going to end up being a little bit lengthier than some of the other videos that we've had. But a lot of this is going to be information we already know, and pictures and diagrams to help us understand, so don't feel like you need to write everything down, every little last bit of detail. A lot of it's just here to help us understand the important concepts. So the concept of a circuit is we want to build a circuit to create an electric current. An electric current refers to a flow of electric charge, just like a river current refers to a flow of water. We measure current in a unit called an ampere, and we use a device called an ammeter to measure those currents. The symbol that we assign current is a I, capital I, and it's defined as simply the rate of change in charge over time, how much charge passes a point in a given time. So an ampere would be a coulomb of charge passing by a point every 1 second. That's a ridiculously large amount of current. Most currents we deal with will be in the range of a microampere, a milliampere rather. In order to have an electric current flow, we got to have two things. The first is a source of electric potential, which is often referred to by its unit name of voltage. What that means is we need something to give charges energy. We're going to refer to that as electric potential energy. And so the source we refer to as a source of electric potential. The definition of voltage is energy per unit charge. So a volt refers to a joule of energy per coulomb of charge. Our example that we typically use is a battery. All cylinder batteries that you know, like AA and C and D batteries, all have the same voltage of 1.5. The bigger batteries just have more coulombs of charge, and so they can provide more energy. So the basic idea is this. The positive end of a battery is full of positive charges. So a positive charge near the end of the battery is repelled by all the other positive charges. That means it's got energy. The way that we measure how much energy it's got or how much electric potential that charge has is with a voltmeter, and we'll do that in class. We're how to connect a voltmeter. The second thing that we need is a place for the charges to go. We need to have some sort of conductive path. Remember that a conductor is a material that allows charges to move through them. Metals are typically the best conductors. Silver is the best conductor that we know of. Copper is a close second. The reason that we make wires out of copper and not silver is just because copper is cheaper. If we don't have a conductive path, then the charges won't move. So charges move very easily through copper. They don't move through something like rubber. We call things that charges can't move through insulators. To kind of understand how charges move through an electric circuit, we're going to compare charges moving through wires to water moving through pipes. So when water moves through pipes, we can use water pressure to do work, the same way that we use charges and electrical potential to do work. So consider a water tower full of water. The reason that the water tower is tall is to give that water lots of gravitational potential energy, something that we know how to figure out. The same thing is true of a battery. Battery gives charges electrical potential energy the same way that a water tower gives water gravitational potential energy. We need pipes to allow the water to move out of the water tower, and the water moves through those pipes. The same way we need a conductive path, such as a wire, in order for charges to move out of the battery. We can put something like a water wheel in the path of the water and use it to do work. The same way we can put a light bulb in the path of those charges and create heat and make the light bulb glow. We'll learn about a few other things we could put in the path in order to make electrical charges give us something more useful. For example, later on we'll learn how a motor works. Now the water wheel is not going to stop turning if there's no exit point for the water that caused it to turn. Otherwise it would fill up and stop turning. And so as the water goes through the water wheel, it's going to lose kinetic energy. Same way as our charges go through our light bulb, they're going to lose electrical energy. And finally, we need to have some place for the path to end. If we cap the pipe for the water, or if we break the electric circuit, then the whole process stops. Charges won't flow, just like water won't flow, and we won't see light bulbs light up or anything like that. So when you're trying to understand how things that you can't see are moving through tiny wires and things like that, a good analogy is water moving through pipes. The way that we measure how well a conductor will actually conduct charge is with a measure called resistance. Resistance is a measure of how well an object can conduct. The better a conductor is, the lower its resistance is going to be. The way that we define resistance is as current per unit volt. The symbol that we give it is an R, and the unit that we measure it in is the ohm. The symbol for an ohm is a capital omega. It's another one of those Greek letters. So that's the symbol for the unit of resistance. In a circuit, resistors are going to do two things. The more resistance there is, the smaller the current's going to be, and then they convert our electrical energy, the kinetic energy of moving charges, to thermal energy. A light bulb is an example of a resistor. As charges move through the light bulb heats up. Electrical energy is being converted to thermal energy. Now the resistance of an object depends on three things. First, what the object is made out of. A way we can measure that is by a quantity called resistivity. The symbol for resistivity is the Greek letter rho. It's kind of like a sideways slanty P. The second thing resistance depends on is the length. The longer a resistor is, the higher its resistance is going to be. We can give that the symbol L. Using water again as our analogy, imagine trying to drink something through a really, really long straw. If the straw is really long, it's going to be very difficult for you to drink through it. The same thing is true with resistors. Long materials, it's very difficult to move charge through. The opposite effect would be the width or the area. The wider a resistor is, the lower its resistance is going to be. Again, use the straw analogy. If you drink through a wider straw, it's going to be much easier to drink. Wider means lower resistance. So we kind of draw a simple picture, like a cylinder shape. That might represent the width. That distance might represent the length, which I misspelled. And charges move in that direction. So if I draw a second resistor, the one on the left has a high resistance, whereas the one I drew on the right has a low resistance. It's short and wide. And so we can build an equation for resistance based on those three things. Bigger length means smaller resistance, so L goes on bottom. Wider means greater resistance. Well, I think I've got that backwards. We should have L on top, area on bottom. So the bigger the area, the smaller the resistance. And then the rho, the resistivity measurement, goes on top. That resistivity is specific to a specific material. For instance, copper has a resistivity, steel has a resistivity, etc., etc. The other thing that resistors do is they generate thermal energy. The rate at which resistors do that, and remember that rate which energy changes is called power, is simply given by the current times the voltage. You can also find it through those two equations, which we'll derive later. So coming back to the measurement of current, what affects it, the relationship between all these variables is referred to as Ohm's law. The greater the voltage, the greater the current, the greater the resistance, the less the voltage, or excuse me, the less the current is. And so this is a really useful law for solving problems and analyzing circuits. In order to better communicate to each other and to analyze what a circuit looks like and how it behaves, rather than just drawing pictures of circuits or describing them verbally, we use circuit diagrams to give us a picture of what a circuit looks like. We use some simple symbols that are common to everybody in order to represent the parts of a circuit. And so here are the 6 symbols that we need to know for right now. A battery, resistor, voltmeter, ammeter, a switch, such as a light switch, and then a wire to connect all these things. Now when we draw a circuit diagram, you need to draw the circuit so that the wires are basically perpendicular to each other at right angles, and they never cross. If you do that, then they should be pretty clear. So for example, suppose that we had a light bulb, which is a resistor, that's connected to a battery and a switch. The circuit diagram would start out with a battery and some wires, and then connect to the switch, which can connect to the light bulb, and then the wires go back to the battery. You didn't have to necessarily draw them in that order. What's important is showing how the current behaves, how it goes from the positive end of the battery to the negative end of the battery. The big side of the battery circuit diagram is the positive side. So if you wanted to indicate that's the positive side. And the small side is the negative side. We talked a little bit earlier about the 2 meters that we're going to need to be able to use in labs to measure potential and current. An ammeter is a device which measures electric current. The way that we connect it in a circuit is it has to be part of the same circuit loop or path as the resistor being measured. We refer to this as being in series. So to draw a simple picture, you would connect an ammeter like that. The current going through the resistor has to be the same as the current going through the ammeter, otherwise the ammeter is not going to measure the current going through the resistor. It'll measure something else. A voltmeter is a device which measures electric potential, or voltage. The way that we connect a voltmeter is different. The voltmeter needs to be connected across the resistor being measured. This is a setup that we refer to as being in parallel. And so a voltmeter gets connected like that, where there's a separate path for current to travel through the resistor and the voltmeter. So we're actually going to set these up in class and learn how to use them, but we do kind of want to have an idea of how they're connected, and later on we'll see exactly why those two have to be connected in exactly that way. So let's suppose, for a simple example, that we have an unknown resistor connected to a 9-volt battery, and we measure the current through it to be 0.25 amperes. Well, if we draw a circuit, it would look like that. If we included the ammeter, it would need to go in the same loop as the resistor, and the voltmeter would go across the resistor like that. So it asks us to calculate its resistance. We take Ohm's law and then solve for R, be voltage over current, and then substituting in numbers, we would get 36 volts per ampere, which is 36 ohms. If we were then asked to calculate the resistivity from its dimensions, its length and its width, we'd simply take our equation for resistance, solve it for the resistivity, plug in our numbers, and we would get something like that. The unit for resistivity, even when the bell rings, is ohm time meter. You can see that one of the meters in the meter squared part of the area cancels out, and so you would get something like ohm per meter. So that's all we're going to discuss in this video today. One thing that you can do to help understand before you get to class is go Google the FET simulator, which is called Circuit Lab. You'd want to pick the one that says DC circuits and just kind of play around with that. It's going to do a lot of the same things that we do in class, but it's something that you can do anywhere. And playing with that simulator a little bit may help you understand before we get into class. Thank you, and that is all.